Hi, I am Al-shdifat, a PhD researcher at Cranfield University, and this presentation is about the development of maintenance ontology for context resolution in Internet of Things enabled diagnostics, with contribution from Dr. Christos Emanuelidis, Muhammad Khan, and Professor Andrew Starr. The motivation for work is on modeling failure analysis of mechanical components to answer queries regarding how faults manifest themselves and how they can be prevented or addressed. This is an example of a critical asset, which is gearbox. Gearbox are used in many applications, including machine tools, industrial equipment, and real any rotary motion power transmission application that requires changes to torque and speed requirements. Failure of gear in these applications can lead to tragic incidents and can have serious consequences on human lives. Therefore, a proactive approach must be adopted that enables such components to be monitored in real time, utilizing predictive maintenance methods. So, there is a strong case to shift from corrective and preventive to data-driven predictive maintenance. IoT-generated data are increasingly considered as an asset, and the data asset value needs to be maximized too. However, asset-generated data in practice are often collected in non-actionable form and need to be modeled and represented to ensure that they continue to function properly and its optimal value over its life cycle. One way to handle data complexity is to introduce context information modeling and management, wherein data and service delivery are determined upon resolving the apparent context of a service or data request. In this paper, ontology-based approaches for semantics maintenance have been proposed as a data and service mediation mechanisms. The underlying ontology of the context resolution mechanism is relevant to failure analysis mechanical components. The terminology and relationship between concepts are structured on the basis of relevant standards with a reliability-oriented knowledge grounding. The approach is applied on a gearbox test rig appropriate for evaluating complex misalignment cases. So, the ontology development 101 is adopted here, based on available reliability standards, such as FMECA or FMEA, failure mode and effect analysis, and has been shown to be well suited for maintenance modeling, and is well documented for implementation in a Protégé environment. Moreover, Protégé editor was selected here as beyond its support for XML and RDF schema and OWL. It also provides a graphic taxonomy, queries in Sparkle, rules in Swirl language, and a built reasoner. The ontology development involves 6 phases, as you can see from this figure. It starts with determine scope, consider reuse, enormous terms, establish classes and hierarchies, establish properties and constraints, and finally create instances. And these steps are outlined next. The initial stage in the methodology is to determine the scope and domain. It requires to define what the ontology will cover, how it will be utilized, and the types of supported questions. The responses to such questions generally evolve throughout the process of constructing the ontology. In this work, the focus of the maintenance ontology is on modeling failure analysis of mechanical components to answer queries regarding how faults manifest themselves and how they can be prevented or addressed, so as to adapt relevant diagnostics or maintenance actions in a condition-based maintenance settings. So the domain of the model is maintenance. The terminology considered for the present work or the present ontology is associated with predictive maintenance. Therefore, The main terminology and the associated definitions are based on consolidated academic literature and mostly on established international standards, such as condition monitoring, diagnostic and maintenance, vibration analysis, asset management, and MIMOSA. The techniques used to define classes hierarchies are top-down, bottom-up, and mixed. So, in this work, the top-down method was employed, in which general classes are added first, followed by subclasses, a process well aligned with asset hierarchies. The process starts with superclasses. For example, the main classes are asset, condition monitoring parameters, and AFMEA techniques. Then, the classes are divided in subclasses. For example, the subclasses for AFMEA techniques are failure effect, failure mode, potential causes, and symptoms. The classes hierarchies alone are insufficient to represent knowledge. They need to be accompanied by three distinct types of properties: object properties, data properties, and annotation properties. The object properties explains the associations among distinct classes. In other words, object properties are verbs that clarify the relation between subjects and objects. And this table shows the properties which their relevant domain and range. For example, the first object property, which is failure cause, has failure cause, and the domain for this one is failure mode, and the range is potential cause. The second one has failure effect. The domain for this one, for this object property, is failure mode, and the range is failure effect, and so on and so forth. Data properties define the different values that an entity can assume in terms of type of value. For example, if failure mode can be detected by one or more detection methods, and these methods can involve certain monitoring parameters. Specific ranges in these parameters may indicate a fault, often a combination with other parameters. And here is an example. These are the main data properties and their domains and ranges. The overall implementation is visualized in this slide. It shows a high-level hierarchy asset. It's a complex equipment that means include several lower hierarchy assets, such as, for example, measurement location, parameters, vibration analysis, oil analysis, collector types, visual inspections, and magnitude, and so on and so forth. Individuals, as you can see here, representing each element in the data set are created. For example, these are some the individuals: bearing failure, failure effects, and so on and so forth. Data properties are assigned to each individual. And finally, object properties are defined between individuals. And as I mentioned earlier, Protégé editor was selected here. Protégé is a free open source ontology editor and framework for building intelligent systems. It's supported by a strong community of academic, government, and corporate users who use Protégé to build knowledge-based solutions. The developed abstract ontology was then tested in the application-specific context of a physical gearbox test rig. Actually, this has been designed for emulating complex cases of misalignment relevant to manufacturing and aerospace engineering assets. Moreover, the AFMEA technique is used to map failure modes, causes, effects, symptoms, and measuring techniques appropriate for giving components and failure modes. Let's move to the main results. A typical usage scenario is that during the undertaking of condition monitoring, queries may be raised to resolve the context of monitoring service. For example, this may involve the determination of possible failure modes for a component, the function impact of the faults on the test rig, the measurement options appropriate for given faults and components, as well as measurement parameters associated with them for the purpose of this implementation, Sparkle queries were built to resolve such queries. Sparkle enables also federated queries over various data sources. Through the following query, we can find what are the main components of a given mechanical machine. As you can see here, this figure shows the results of the query to identify the main components of the asset type. These components are bearing, coupling, lubricant, rotor, sails, and shaft. Another query can be applied to answer what are the functions of the main components of the test rig. This table shows the results of a query to identify the functions of the main test rig components. This query can be useful to a maintenance engineering in order to link faults to functional impacts as shown in this table. For example, this is the component, the main component, for example, coupling. The function for this one, the function of coupling is to connect to shaft. Moreover, the present implementation allows a query in the maintenance ontology to resolve key analysis characteristics such as component function, failure mode, failure effects, failure causes, severity, detectability, and RPN, as you can see from this figure. The outcomes of the work can be used by industry to drive their maintenance services adaptation. Here is an example of context-based service adaptation, listing some of the most common faults expected to occur and matching them to the parameters or technique possible to monitor in order to show the occurrence of faults. In this regard, context-based service adaptation can help maintenance engineers narrowing down the list of options in machines monitoring. Here is another example. A component that has high significance in failure analysis is the bearing based on the AFMEA analysis. Therefore, another query can be applied to determine symptoms and fault severity, but also determine the faults with highest diagnostics potential. Consequently, the most critical failure mode is a fracture, as you can see here, and the typical failure mechanisms for this is fatigue. And here is the symptoms and severity and diagnosis. Finally, the last step was the validation of the ontology. This involved applicability, robustness, and level of details evaluation. Applicability: to what extent is the ontology applicable to real case scenario, as I have mentioned earlier. Assess the true validation by examples on real case scenario. To assess the model robustness, a number of queries have been constructed in Sparkle and tested on the ontology model. The process was considered satisfactory when all tests were shown to produce satisfactory responses for the given operational scenario. The level of details of the model correlation with its fidelity, and it's evaluated by strictly following a consolidated procedure for ontology engineering and AFMEA technique. In the present work, modeling is guided by the Ontology Development 101 process. Let's move to the conclusion. Context management was considered on the basis of valid knowledge constructed for interoperability and context-based service adaptation. So, the aim was to produce a semantic organization of data so as to drive maintenance services. The approach was applied on a gearbox test rig, appropriate for evaluating complex misalignment cases. While the application focus is quite specific, the ontology abstraction level is actually such that it could also be implemented on other application cases, as it offers a sound baseline for further customization or extension. The research is ongoing, and next steps have already included employing reasoning to resolve the context of a service request, but this is not included in this paper. On behalf of co-authors, I wish to thank you for the interest in this work. Thank you so much.